thinking, I already know all about knots. I use them every day, like the knots I use to tie my shoes, put on a tie, or close up a trash bag. Mathematical knots are actually a little different than the kind of knots you're probably used to. So what exactly is a mathematical knot?
A mathematical knot is the shape that results when you take a line, wrap it around itself in any way, and then seal its two ends together, forming a continuous closed curve.
There are infinitely many different knots we can create. But we consider some of these knots to be the same. Knot equivalence is an important part of knot theory. Two knots are considered to be equivalent if one can be manipulated to look like the other, without breaking the strand, but just by moving it around. This knot is called the unknot. It's a simple closed circle. We can find a lot of knots that at first look different from the unknot, but we are actually able to shape them into the unknot just by moving them around. A knot's ability to be untangled like this is an example of knot equivalence. As a child, you may have played the game known as Pretzel, or Human Knot, and this game is really just an example of equivalence to the unknot, because the original tangle of people is moved around until it becomes the unknot, without anybody letting go. When we move knots around like we just saw, we can simplify the shifts made into a sequence of 3 specified movements known as the Riedmeister moves. They are the untwist, the cross, and the slide. Methods used to test for knot equivalence are called knot invariants. One simple knot invariant is tricolorability. This invariant involves coloring segments of a knot in using 3 different colors. A knot is tricolorable if it can be filled in such that 1. Multiple colors are used, and 2. Each crossing has 3 same colored segments or 3 different colored segments. This is a knot invariant because of the property that if a knot is tricolorable, any of its equivalent knots must also be tricolorable. For example, the unknot is not tricolorable. This means that if any given knot is tricolorable, it cannot be equivalent to the unknot. Another knot invariant is the Alexander-Conway polynomial, given by this formula here. Let me explain how the function works. It's recursive, meaning the function itself is used in its definition. For the unknot, the value of this polynomial is 1, and for other knots, the polynomial is defined by choosing any crossing in the knot. L plus represents the current knot, L minus shows the same knot but switching which strand is on top in the chosen crossing, and L0 is the knot with that crossing eliminated. Filling the polynomial's formula out for the trefoil knot gives us a final value of 1 plus z squared. We know that the unknot's polynomial value is 1. Since these two values aren't equal, we know that this knot is not equivalent to the unknot. We have just proved that the trefoil knot can't be untangled. Knot theory has many significant applications, as it can be used in researching the knotting behavior of DNA or to aid in quantum computations. It's definitely not something to be forgotten.